Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to parse arithmetic expressions. So I'm going to go here. Let me close some of these. I'm always doing work, so I end up leaving a bunch of files open from the last time I was coding. So basically today we're going to learn about how to process math expressions. So if we go to our grammar file, and we look here, so we can see we have all of these various expressions for math expressions, control flow, you have and, or, so on and so forth. So let's just kind of see how we actually process this. So before we get into that, I actually have something I want to show you guys. So if I go up here, so basically what this is this is called the levels of precedence. Now, by no means is this the tried and true way of how you should build your programming language. You guys can do whatever you want. My language is pretty advanced, so I kind of set it up in this way, but I'm just some random guy on YouTube, so just take what I say today with which you may. Most of the things that I'm going to say today, though, I would highly recommend you do because it just kind of makes sense. So let's kind of look through this and see what we have. So at the top level, and the way it works before I get into it, so the higher level you are, the lower the precedence, and the lower the level, the higher the precedence. Meaning that precedence basically means, in short, I'm not going to go into the theory behind, how you process math expressions and why certain things should be before the other. I'm just going to keep it straight and simple because I know that if things get a little too complicated, I just check out. So basically, preference means how important is each thing to the compiler. Meaning, like, let's say, you guys learned in class, right? Where when you first started learning math, you learned this phrase called PEMDAS. Please excuse my dear Aunt Sally. And that's kind of formulated here. So we can see here, now Unary is its own case, that's why it's kind of in its own box. But you can see we have our parentheses. Now, technically speaking, we have a massive amount of precedence already set, and you guys are already learning tons of crap that like I'm not even mentioning. Like if we were to go to like an official language specification, there would be tons of stuff in there that you're already learning by virtue of just watching this video and the YouTube series. But I'm trying to keep things very simple, so I'm not going too in-depth into detail. But if we look up here, we can see we have our primary expression. We process expression or parent expression values in there. So, I mean, parentheses is already one of the higher precedence values. But technically, if you look here, right, like what has the highest precedence? The highest precedence, technically speaking, in terms of parsing expressions, would be a pre-increment, plus, plus, or minus, minus. Precedence after that, in terms of importance, would be literals, and then, utype.class, and so on and so forth. I don't have to go through everything. But what's important in the PEMDAS example is that we do process parenthesis expressions inside of here. So that's the P in PEMDAS. Now let's look at the rest of the letters. So we have E for exponent. This is a double multiplication symbol. So that's what I literally just added this like a few days ago. But that's why I mentioned that in the previous video. So if you guys want to see how to implement this exponent keyword, then I would definitely recommend you check out my previous video. I go over that at the beginning. But yeah, so this is the exponent part. This is the multiplication part, or PEM DAS. So this is the M and the D, multiplication and division. Then you have addition and subtraction. So this is your plus and minus. And then the rest of this garbage is just like stuff for programming languages, right? Like math doesn't have control flow. Like this is stuff for like computers. But even though, so like I would recommend at a minimum for your programming language, depending on what you're going to do, just have this in this order. Like you should have unaries as the highest level precedence, then exponents, multiplication, addition, and subtraction. Um, After that, though, I mean, in my opinion, this makes sense, right? So if we look at it, right, we have an and expression. So if we have like, I don't know, if, and let's say we have, whoops, why did it do that? So if we have like a number, right, num is equal to 10, we can say if num is less than 10 and num is greater than 5, right? So that means it has to be a number between 5 and 10. Then that, I mean, it makes sense to process this first. And if this is true, then process the right expression. And if that is both true, then return 1. Otherwise, if this is not true, just return false right off the bat and don't even execute this code. So if you look at it, right, you have and this also goes for or, right? So, we could have or here, or we could say like, num or we could say num or 10, and we could say greater than 10, right? Is that even legal? Yeah, so like what we could do is we can do what's called a bitwise shifting. So we can like basically take this number and do an OR on it and then see if that value is greater than 10. So that's another reason why we want to do this, because what if you do like bit shifting? Also, if we look here, like what if you want to say like, X is, or like some field is not equal to null? Well, you need to have that before and. So this order just makes sense, right? And then of course you have your left shift and right shift and everything. So I would just highly recommend you kind of keep this order. And in fact, I'm actually going to go here really quick. So I actually pulled all of this information that you see here in this graph that I made for you guys. I pulled this straight from this website. So when I first built my programming language, I modeled my programming language originally after the JavaScript programming language. When you guys are building your language, you need to not reinvent the wheel. Like if you're going to obviously solve some problem with your programming language, or maybe you're just trying to do something different that other languages don't do and like offer tons of features, you want to model your language or pick a language that it's going to closely be related to. And in my case, it was JavaScript. My language is now related to like 5 or 6 different languages at this point, but when I started out, it had its roots in JavaScript. So if you guys go to this page here, I'm going to put this link in the description. What this does is this goes into the theory and just kind of explains what operator precedence actually is and what it truly means to have operator precedence and why things are the way they are. So I'm not going to go into it in too much detail. For the most part, I think it makes sense. You need something to the left, you need something to the right, and you have an operation that you want to perform. That's kind of how I view it. I like things to be simple, but like I said, if you guys would like to read this page, then I will have that link in the description below. So what's important with this page out of everything else is this table here. So we have this table, and you can see here it has various different like types of things that you process, right? And it has like, new, delete. Um, when we get down to here though, this is what's important. We have addition, subtraction, left shift, right shift, and all of our various PEMDAS characters. So we have, exponents, multiplication, division, addition, subtraction, that's your PEMDAS. And then of course, you process parenthesis expression. So like this is grouping. What this is this is like a parenthesis expression. So this has the highest precedence of everything else in their language. Again, like when it comes to everything else, like new statements and everything, you can put in whatever order you want. But when it comes to doing math, put it in this order. So let's actually look at some of the code to see kind of how this stuff is implemented. So what you're going to want to do is you're going to want to create a binary function. And in that binary function, I mean, most of the stuff is pretty straightforward. So we have like this binary function here, and that's going to represent a binary expression. Now, if we look here, you can imagine this like a hotel, right? The highest level is the highest or the lowest precedence, and the lowest level is the highest precedence. And because we're using recursion, which I highly recommend you do, I wouldn't recommend you flattening this processing here. I'd recommend you use recursion for this. We are going to do it in that order. So we're going to start off with and or, and literally every single function from here on out is going to look exactly the same. So I'm just going to go over one, and then we can just kind of look at the others. So if we look at the first one, we can see here we have a Boolean called success, and we need to process our left expression. So what is going to be to the left side of our and or, XOR or whatever we're processing, right? So what's going to be to the left of our expression? Then what we do is we create a while loop, and we just loop for as many times as possible, because it's entirely possible that you could say like, num is equal to 5 divided by 5 times 6, whatever. So all of these symbols, now I know this is and or, but like for instance, if we had, I don't know, like division down here, right? You could have multiple of those characters. So you just want to support that in case they're like back to back. And what you do is you create this match function. Now, this one's pretty cool. I actually got this from Stack Overflow, so I'm not even going to pretend like I know exactly what the fuck this function does. I just copied the code. So You guys can copy it down too. Basically, what it allows you to do is in C++ pass a dynamic amount of arguments to a function, and then you basically can iterate through those arguments and process them. So the way it works is you create what's called a VA list or a var arg list. Then you need to start the var arg, and you need to make sure that the number of args is correct based on how many arguments you actually passed into the function. You create this for loop here, and you need to create what's called a var arg, and that's going to represent the actual argument that you're processing. Now you need to make sure that the type that you're putting as the var arg is exactly the type that you're passing in for every single argument. Otherwise, you're probably going to get a segfault. So just be mindful of that. In our case, what we do is we just check to see if the next token is equal to any one of these tokens that we pass in, right? So we get the type of the token and we check to see if the next token is equal to any of the types. If so, we say found is equal to true and we break. We end the var and we return found. Now the reason why I don't return true here immediately is because you need to end the var args. So you just want to make sure you do that and release up that memory. So yeah, that's kind of why I do that. So let's go back up to our function. And we can see, all right, so we support 5 different tokens for this specific function here. So we support and XOR, or and or. So these are what's called bitwise operators, and these are what's called binary operators. The difference between a bitwise operator and a binary operator, and we'll get into this later, but bitwise operators allow you to manipulate and read and or write bits inside of a number, while we have our traditional binary operators that allows us to basically evaluate an expression based on 2 values to the left and right. So we have in here, you need to do a check. So we have a is expression symbol peak at 2. Now the reason why you want to do this is you want to protect from and I actually just fixed this yesterday. So like let's say we have like a simple function, right? 2 plus 2, right? Num is equal to 2 plus 2. Well, what based on the code that I have, what you could technically do, since I have a while loop, just say 2 plus plus 2, and you can space them out. Now, obviously, if you do like 2 plus plus, that's gonna, be basically adding 4, and then you'll have 2 after that, which you'll still get a exception, or like some type of error in the parser, but it could be a little more complicated where you have like 2 divided by, 6, and then, I don't know, minus plus, right? So here's a better example where minus plus isn't any direct symbol, it's just 2 characters. So you want to make sure you don't allow the user to do that, and you say expected expression if there are exactly 2 characters following it, because as you know, the match checks if the next character is equal to our actual token. So if we have 2 characters equal to expression symbols, then that's bad. After that, we check to see if the ast.subast is not equal to empty. Now, the reason why we want to do this is we will see this later on, but basically, as we're going through this while loop, what we effectively do is we have like this, right? So here, I'm going to do this. So let's say we process our left expression of 2, right? Now we're inside of this while loop. Now, if we have like a 2 plus, and then let's say we have another 2 here, well, what if this isn't 2? What if this is, I don't know, some mess, right? Like a bunch of like random stuff, and then we have like our plus symbol. Well, when we go to process equality, if we scroll all the way down to the last function in this like hotel, I guess you could say, of function calls, we try to parse a primary expression. And if that primary expression does not succeed, we free up this last sub. So there's technically a chance where we might not have something to process. So you just want to make sure that we are processing both a left and a right expression. So if it's not equal to empty, or if it is equal to empty, then we return false. Otherwise, we get the left expression from the last sub AST from the AST pointer, and then we basically pop that back and we create a branch underneath, we create a branch underneath this AST called AST and expression. Then we add the left branch to this branch here. Now I know you're probably wondering, well, why don't we just encapsulate it? There's a reason for that. You don't want to encapsulate it because you want it to be like, you want it to be a left and right kind of thing. So you want to say 2 plus 3. Encapsulation typically just eats everything inside of the AST list. you only want to get the next leftmost AST. You don't want to eat up every single other AST that we're going to process. So that's why we don't use encapsulation here. So yeah, after that, you want to advance. So now you finally want to consume whatever token we're processing. We consume that token by adding it to our branch. Very important because we need this for processing it later. We call equality, which is the next rung down, and then we say success is equal to true. Now, if we process equality and let's say we process the left expression and it fails, and we also don't have, an expression or a symbol here to process, then of course success will return false. So we just want to make sure we're returning the appropriate value, because up here, we're going to use that success variable to basically show whether or not we successfully processed a binary expression. So that's very important. But yeah, so that's pretty much it. Literally every single function, like I said, is the exact same. So let's just quickly go through the functions so we can actually see how this code looks on the back end. So if we go down one rung, so now we're going down one level, so we're on the next level here, we're looking for equality. So we want to have the equality function where we basically just parse equal equal and not equal. So both of these characters here. Same code here, same code there. The only difference is the branch. So between all of these functions, the only thing that's going to be different is what tokens are you processing and what is the name of the branch. Everything else is exactly the same. So we are processing these characters here and we're processing an equals expression. Next level, we have a comparison. So we process greater than or equal to, less than or equal to. And then we process a less than expression or a less expression. After that, we have shift. So, we're doing everything correctly. So we have and comparison or equality here. Then we have, what was it called? Less than, or it was called comparison. Next, we have shift, which is a left and right bit shift. So we have shift left, shift right, and we have AST shift expression. After that, we have addition. So now we're here, plus minus, AST add expression. After that, we have multiplication, divide, modulus, and multiply. And we have an AST multiplication expression. Finally, we have, well, I guess not last, we still got to do unary. So we have our exponent, which is going to represent the exponent character, which again, if you guys did not add this, I will put the link in the description so you can go check that video out. But that is the double multiplication symbol, and that turns out to be a AST exponent expression. So finally, we're finally at the last rung. So like, when we're processing our left expressions, we're constantly just calling like the next level, and we just keep doing that. Eventually, we're going to get down to here and process this. So we're going to need to create flat out a branch of AST expression. Now we're going to have the code for processing our plus and minus. Now, what a unary operator is versus a the difference between a unary operator and like a binary operator is that unary operators are expected to act on a single thing, right? So like if we say, negative y, right? And let's say y is equal to 305 or something. This will effectively return negative 305. Now I think that was actually an error, wasn't it? Okay, so I have plus and minus here. I actually only support minus and not. It doesn't really make sense to have a plus unary. If they want to have an absolute value, they can call like, I don't know, math.abs once I create my math API library in my standard library. But for now, I only support minus and not as unary operators. So I'm pretty sure you guys know what not does, so I don't have to really go over that. So in here, we basically advance one token, we consume whatever unary token we're processing, we call a unary, so we call back into this function dynamically, because obviously we're at the last rung, so we just call the last thing, and then we say branch set AST type AST minus expression, and then we call not. Now the reason why you don't want to call like binary, like go way back up to the top, is because we want to just parse a primary expression when we get down to the bottom, right? Because with unary, you don't want to do any math. You want to just do something on a specific expression. So if you're going to say, not y, well, you're going to need to process an expression here immediately. You're not trying to do any math. So we set the type of the branch to an AST minus, so we reset the type of the branch. and that will contain all the information that we need. And of course, we return success based on whether or not we successfully parsed our unary. Same thing for not. It's exactly the same code. I don't have to go over all of it. You just want to make sure you support the not token and AST minus expression. Now, I'm sure some of you are wondering, why do I call parse primary expression and not parse expression? You see up here, I have this AST underscore expression. There's a reason for that. If you think about it, if you scroll back up to the top, if we go call parse expression, then we go down to here to call parse a binary expression. If we couldn't, for whatever reason, parse a primary expression or left curly or whatever, when we go all the way down to here, we're going to end up with a stack overflow exception because we constantly keep calling parse expression to figure out what we need to process. This is another reason why you want to put the vast majority, if not almost every single thing that your language is going to process inside of parse primary expression. So just keep that in mind. So what we want to do for that is we want to enter protected mode because we're not guaranteed to process anything. We want to store the current token so we can reset it later. And yeah, so I mean, this is the same code. We've seen this type of code before. So if the thing that we're trying to process is not successful, then we ignore any errors, we reset the token, we free up the sub. Now, here's what's important. You want to say ast.freeLastSub. You don't want to say branch.freeLastSub. You want to free this actual branch that was created. And if you say branch.freeLastSub, this branch will never get freed because it's underneath this AST pointer here. So you want to call the AST and free up the last branch for that reason. And it'll also end up freeing up this token that was created underneath this branch as well. And of course, you return false if you didn't successfully process it. Makes sense. Otherwise, you fail if there are any errors possible, and then you return true. So that means you've successfully processed a primary expression. So let's scroll back up to the top and let's see kind of how this stuff looks. I'm gonna do this. So I'm gonna start off simple. So 2 plus 2. So if I hit play and actually run this, we can actually see what the output of the compiler is for this expression. All right, so we get 4. Now what this code is if you guys are wondering, this expression code here is the generated output of the virtual machine code that we're going to be executing once we build our virtual machine. So I'm still working out the instructions right now, but this will effectively be the machine instructions that we're going to be executing for our virtual machine. Now let's do an example where we can like see or force PEMDAS to happen. So we can see here, let me do this. So let's do like multiplication and then division. So if I say 4 times 2 plus 2, if I do something like that, based on the rules that I have and the order of precedence, what should happen is we should say first 4 times 2, which is 8, and then plus 2, so we should get 10. So let's make sure that that is correct. Yes, so we get 10. But now, if we do something like this, we should get a different number. So now this is going to be 4 times 4, which now should return 16. Yep, so it looks like it returned 16. And the reason why it does that is because the parentheses changes the precedence order, and it forces the compiler to say, okay, this thing in the parentheses, prioritize that first, and then process everything else after that. So now let's get a little bit more complicated. Let's say we have like, 2 to the power of 2, which would be 4, and then we could say, plus 2 divided by 2. So 2 divided by 2 is 1. So based on our ordering, right, we have our exponent, multiplication and division, and then addition and subtraction. So with that order, we should do this first. So we should say 2 to the power of 2, which is 4, plus, is that right? 2 to the power of 2, no, so that's incorrect. So we should do 2 to the power of 2, and then we should do 2 divided by 2. So we should basically be doing 4 plus 1, and that should give us the value of 5. Yep, so looks to be correct. So yeah, that's pretty cool. This is why order of precedence is important. So now I'm going to completely radically change it and see what happens. Whoops. All right, let's see what the output is. Okay, so we still get 5. I guess that's correct. Now, here's one thing. Now, I know it's a bit early in the programming language, but here's something that I typically do when I try to like check my sanity in terms of if I'm doing things correctly. And this is why I said earlier in the video, when you start building your programming language, you need to model it after another language, at least syntactically wise, so that way it can be easier for you to test and translate various different expressions. So because mine is modeled off of JavaScript, I'm going to look for a online JavaScript compiler. And typically where I like to go is I like to go to playcode.io. You guys can pick whatever you want. But I typically go here and then I just run a couple tests to see like, am I doing things correctly? So I'm going to say console. What? Okay, I'm just going to copy this code here because I'm lazy. So let's look at the expression. So I'm going to copy this code and make sure that it's correct. So if I go here, and even with this code, all right, so it looks like we have 5. Now let's do some retarded stuff. Let's just like put in, I don't know, some wacky number divided by, this number modulus this number plus this value times, something else. Oh, okay, well, I guess I got not a number. I guess I put too many. Okay, that gives me infinity. Jesus Christ. Let's say 2 to the power of 2 divided by 13 times 4 plus 2. And let's put this value into parentheses here. Whoops, did I mess that up? All right, so we should get like 6 point something. All right, so let's see what my compiler actually outputs. So I'm going to put this here, and we get 6.67519. And that is 6.67518. Okay, so that's pretty close. So yeah, looks to be correct. And yeah, so let's actually see how this code is generated. So we can see how our compiler actually knows how to do this stuff. So I'm going to do a simple example again, go back down to 2.2 and hit play and go back up to the top, and we can see how this looks. So we have our block, our statement, our expression, our add expression. So we're only doing adding, so we're only going to have one high level. What I typically like to call this is I like to call this the God expression, meaning that like the God expression is pretty much going to be the start of the ripple effect of all the things you're going to process, and we'll see what that is in a little bit. So we have our add expression, we have our 2 plus 2. So that looks to be good. We have two expressions here and the add expression AST. So now let's do 2 to the power of 2 plus 2. Now what that's going to do is we're going to have a God expression of 2 to the power of 2, and then we're going to have a secondary expression of plus 2 after that. So if we look here, you can see here we have, oh, okay, so I guess add is the God expression. All right, well, I guess I was wrong. So we have our add expression, and then we have our exponent expression of 2. So we have two exponent expressions, which makes sense, or we have two add expressions, which makes sense. So in our exponent expression, we have two additional expressions of 2 and 2. So we have 2 here, 2 here. Now I know I have a bunch of 2's everywhere. Let's like make this stand out. Like let's say 2 to the power, or let's say like 3 to the power of 2 plus 4. So that way we can like know where everything is. So if we look back, we can see here we have our add expression, we have our exponent expression, we have our 3 to the power of 3. What the I thought I put 2. Okay, I'm just going to leave that in. I'm not even going to edit that out. So we have our expression, we have our 3 to the power of 2. That looks good. And then we have plus 4. So if we look here, the plus is, the exponent expression, whatever the value of that is, plus this expression of 4. So that's kind of how that works. Now, let's see what happens when we put parentheses. Now, instead of like doing 3 to the exponent or 3 to the power of 2 and then adding 4, we're going to force the compiler to add these values first and then take that value and use that as the power of what 3 will be. So run here. And in here we can clearly see why it works, right? So we have our left expression representing 3, and now we have our right expression representing a parent expression, which is 2 plus 4. All it is an add expression of a left value of 2 and a right value of 4. So now let's do some more. So let's say divided by 10, and then let's see what other values do we have. So we're doing like math. And then let's say and 3 plus 1. Let's see how all of this is going to look together. This is kind of an interesting, what does it turn? Okay, so it returns 1, which is fine. So if we look here, we can see that we have our AND expression as the God expression, which makes perfect sense. And then in the AND expression, we have two major expressions. So we have our left and our right expression. So our left expression is going to represent a multiplication expression, I guess. And that expression is going to have two expressions inside of it. Oh, okay, so I guess that makes sense. So we have like this 10 here is like our right expression, then all this stuff is like our left expression. So I guess that makes sense. So we have our power expression, our exponent expression here of 3 to the power of, and then we say our parent expression of, where is it? 2 plus, this is all screwed up because I guess there's too many letters. 2 plus 4. So that looks to be good. And then we have, after the and, we have our 3 plus 1. So if we look here, we have our secondary expression. So here's the right expression for the and value. And then we have our AST add expression of 3 and 1. So we have 3 here and 1. So that looks to be good. And if we follow this all the way up, we can see here that that resides inside of this and AST. So it looks like it is, in fact, the right expression pertaining to this specific operation that we're doing. So that's going to be it for today, guys. Hopefully all of this made sense. As usual, if you guys have any questions, definitely write them in the comment section below. And of course, if you guys would love to help out the channel, definitely head over to androidevcd/sharp. And this is the main repository where my project is developed on a daily basis. And when you guys get over there, definitely watch, star, and fork this repository. That's going to give this repository a lot more visibility and let other developers know this language exists. Also, if you guys are interested in kind of looking at some of the things I do on a daily basis in terms of updates and bug fixes, you can check out the remastered branch. Anything other than master or remastered aren't used, so just keep that in mind. And once you're there, you can check out, there's a couple different things. So you can check out the commits, and I write some pretty wordy commits, so you can kind of get a gist of what I'm doing without really having to like jump into the code. And I've lately been pushing updates pretty regularly, some pretty big ones. Um, and also, if you guys are interested in maybe learning about things that I've done in the past in terms of updates, bug fixes, so on and so forth, you can check out the bin folder, or no, actually, it's the doc folder. And in there, there's two main files. You can check out the change list file. That's going to be pretty much everything that I've done to the language in the past. Every time when I put out a new release for the language, I update this file, and I don't update it very frequently, so this one's pretty outdated in terms of like all the stuff that I've added so far. And then you can check out the roadmap file. Now, this one is the most up to date in terms of everything that I've done to the language. And not only that, it also contains stuff that I'm looking to add in the future. So highly recommend checking out this file. Gives you a lot of insight into the language, so on and so forth. Also, if you guys are new to the channel, definitely consider subscribing. And until next time, I'll see you guys later.